Section 1.2 is an exploration with patterns. So what we're going to take a look at today is some different kinds of patterns that can occur and how we handle them when they do. So before we can get to the pattern part of this, we need to talk about a little bit of vocabulary. A conjecture is a statement or conclusion that has not been proven. This word comes up sometimes in questions, and everybody's like, what does conjecture mean? It just means, what do you think is happening? What is your best guess of what's going on? Okay? So kind of think about it like as a theory or a hypothesis in science, right? You're testing it, you're trying to see if it's going to work. A counterexample is something that shows it doesn't work. It proves that it's false. And now there are two types of inductive reasoning, or two types of reasoning. The first one is inductive. Inductive reasoning is a method of making generalizations based on observations or patterns. And then deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true, and logic for proof.
What do you mean by axioms?
Statements that we don't prove. So like when you do geometry, there's a lot of things in Euclidean geometry, things that you don't ever actually prove, like things you define but you don't prove. Like for instance, when I tell you a point is this, I don't have to sort of prove to you that's what a point is. It's just the definition of the point. So it's like that. One of the axioms of Euclidean geometry is that when you have a line and you have a point not on the line, there's exactly one line through that point parallel to the first line. But it's not something that can be proven. It's something that we just have to take as true and go with it. Okay? All right, inductive reasoning is the kind of reasoning that you probably use every day. Inductive reasoning is what told me that the reason that the handle was sticky on the door was because my son threw a banana out in the garage and he had a banana all over his hands when he touched the door. Right? I looked at what's going on and I tried to make my best guess as to what's happening. That's inductive reasoning. All right, now we're going to use some very specific types of inductive and deductive reasoning and decide which one's which in a little bit, but we'll come back to that, those definitions when we need them. A few more. Sequences. Sequence is an ordered arrangement of numbers, figures, or objects. Now we in this class are going to work with them with numbers, but when you first start working with sequences with the little bitty ones in preschool, you usually use shapes or colors, right? It goes red triangle, blue square, red triangle, blue square. What comes next? Okay, so sequences are done from a very early age. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given, and a rule that shows how to obtain each successive term in the sequence. So a recursive formula says something like, take the previous result and multiply by 2. So there's not an equation necessarily, but I have to have a previous result, and I have to know what to do with the previous result to get the next one. I got to have two pieces of information, really, right? The first or previous result, and then the pattern for what I do to get the next one. And then the nth or general term is actually a formula that can tell you how to get the nth term with no prior information needed. So this would be something like the sequence is all the even terms. So the equation, the formula is 2 times n. So if you want the first term, you plug in 1. If you want the second term, you plug in 2. If you want the 55th term, you plug in 55. Okay, that doesn't work very well for recursive formulas. If you want the 55th term, you got to go through all the first 54 terms to get the 55th term. With a general term, you actually have an equation that you can plug 55 into to get it. Okay? Now we're going to look at two specific types of sequences in depth, and then we're going to talk about at least one more after that, less in depth. The first sequence we're going to take a look at is called an arithmetic sequence. This is a sequence in which each successive term is obtained from the previous term by the addition or subtraction of a fixed number. So I'll give you an example. 4, 7, 10, 13, and so on. What would I have to do to get the next term? What's the pattern? Add 3, right? Let's add 3. And that adding of 3, and it doesn't have to be addition, it could be subtraction. I could be subtracting 3 every time if I flipped this around. That 3 is called the common difference. It's the fixed number added to or subtracted from previous terms to get the successive terms in an arithmetic sequence. And we use the sign, so we write down plus 3 or we write down minus 3. So if we were subtracting 3, we'd actually say the common difference is negative 3, to be clear, okay? So maybe I should just say it's the fixed number added to when we talk about positive and negative numbers, but at any rate, keep the sign. So this is arithmetic. The next type that we're going to look at in depth is called geometric. So geometric sequence is a sequence in which each successive term is obtained from the previous term by the multiplication of or division by a specific number. Again, we'll give you an example. 108, 36, 12, 4, and so on. Is it multiplication or division here? It's actually division, right? What are we dividing by? 3. Now, I'm going to write this a little bit funny. Instead of writing it as, well, I'll write divided by 3, but I'm also going to write down that that means the same thing as multiplying by 1/3. Are you guys with me? Okay. They define this as the multiplication part. So really this shouldn't maybe necessarily say divide. The common ratio is considered to be the 1/3. It's the number that's multiplied by it, not really divided by, but the multiplying or dividing is the same thing in mathematics.
Yeah, I want us to write in, like, on answer the fractional, like, always multiply by.
Well, yes, because their common ratio is actually more about the multiplication factor that's being used. Yeah. But again, Emily, if I like switched this diagram around and I went 4, 12, 36, 108, then it would be 3. So we would want to write down 3 in that case. Okay, and then the one more small sequence, and we're not going to talk too much about it, but it occurs a lot in nature. It's called a Fibonacci sequence. A Fibonacci sequence is not arithmetic and it's not geometric. And it follows a different pattern common in nature. So I'm going to write down the first few of these. Who's heard of Fibonacci sequences before? Okay, most of you. Do you guys remember how you get from one term to the next? Or do you just remember the name? Okay, well, let's see. Maybe you'll pick it up once I write it down. Okay, the pattern looks something like this. This is the pattern. It's obviously not arithmetic, because what would it need to be arithmetic? I need to be adding the same term, and that obviously doesn't work since the first one's 1, then 1, and then I get 2. So that's no good. Not multiplication either, right? So it's not geometric. Same thing, 1 to 1. I can't get to 2. So I get stuck really quickly. Does anybody remember what the pattern is for getting the next number? Okay, so I'm going to say it a little bit differently than you just did, Emily. But basically, wherever you are in the sequence, you add the previous 2 numbers together, right? So if you take a look right here, if I add 1 plus 2, I get 3. If I add 5 plus 8, I get 13. So if I wanted the next number in the sequence, what would I have to do to get it? 8 plus 13, which would be 21. And then we would keep going. Okay? So this is a Fibonacci sequence. And this feels like a funny thing to put sort of in the middle of all this talking about sequences, but it's going to come into play in a minute here. So just, it's one of those prior knowledge things that I want to make sure that we remember. The definition of exponentials. So if you have a to the n, if n is a natural number, then a to the n is a times a times a and so forth, n times. And if a is equal to, I'm sorry, if n is equal to 0 and a is not 0, then a to the n, which is equivalently a to the 0, equals 1. And for those of you who have taken proportional and statistical reasoning, I proved that in proportional and statistical reasoning, but we're not going to do that today, okay? So just take it as a fact for now. So this is not an axiom, Emily, because it can be proven, okay? But a, for now, we're just going to take it at face value. A to the 0 is 1. Okay, so let's take what we have been discussing and do an example with it. This is example number 1. List the next 3 terms in the sequence. Identify if the sequence is arithmetic, geometric, or neither, and then find the nth or the general term for the sequence. Okay? So the first thing is the easiest one. Figure out what the pattern is and then figure out what comes next. So for the first one, 1, 4, 7, 10. We already did this one because that apparently was on my brain when I created my last example. What comes next? 13, 16, 19. Hope you're saying 19. Is everybody saying 19? Okay, good. All right, so this is what we have. The pattern is that we add 3. We already did that, so I'll just write that down. Now, the adding 3 part, the part that I just put plus 3, that doesn't answer any question on this page. Okay? That's for our information to continue forward. So, this is part A, right? All right. Part B, then. Part B says that we are supposed to find if it's arithmetic, geometric, or neither. So which one is this? Arithmetic. And if it asked you to identify the common difference, it would be 3, right? We added 3. Now, C is the part that we haven't done yet. We haven't even talked about how to do it. We want to create the general term. That is, we want to create an equation so that when they ask me what's the 55th term, I can just find it instead of having to add 3 until I get there. Because that's not a very time-effective thing to do, right? It would be better if I had an equation I could plug it into. So how do we create such an equation? Well, let's think about what we know about arithmetic. This is adding a bunch of 3's together eventually, right? I get plus 3, plus 3, plus 3, plus 3. How do you do that faster? Close. Not powers. That's exponents and powers are the same thing. We're going to get there, but not on this problem. Multiplication. When you add something together a bunch of times, that's the same as multiplying, right? If I want to add 3 together 7 times, I am not going to add 3 together 7 times. I'm going to multiply 3 times 7, right? It's multiplication. So that 3 that we're getting in here is going to be multiplied by the n term that we want, 3 times n. Now, you're going to check and you're going to see if I plug in, and I don't care which number you pick, I usually just pick the second term. So I would pick 4 here as my second term. If I plug in the number 2, because it's the second term, does 3 times 2 give me 4? No, it's a little too high, right? How much too high? 2. So you know what I'm going to do? I'm going to do minus 2 on the end. That's it. However high or however low I am, I'm just going to add or subtract the number there to compensate. It's just a compensation. And you can check to make sure you're right by taking another term. So let's say that we take the term 4. Okay, the 4th term should be 10. If I plug in the number 4 here, what's 3 times 4? 12 minus 2? Do we have the right equation? We do. We do. Okay, so it's all about multiplication, and then it's guess and check, right? Kinda. I mean, we're adding or subtracting whatever we need to on the end. Okay, part B. What's going on part B? They're multiplied by 2. All right, so what comes after 24 then? 48, and then what? Can you go that high? 96. And then what? 192. Okay, so this is part A. Part B, geometric, arithmetic, or neither. This is geometric. And then part C is the equation. Again, the part that I haven't shown you how to do. All right, this one will not be the same as the last one because it's not arithmetic. All arithmetic sequences will basically be like the last one. It'll be the common difference times n, and then plus or minus something. But geometric doesn't do that because I'm not adding 2 every time, I'm multiplying by 2 every time. So again, if I multiplied by 2 5 times, I really would not want to do 2 times 2 times 2 times 2 times, I don't know, I lost track of my 2's, but I wouldn't want to do it 5 times. It would be easier to use exponents, like you ladies were talking about on the last one. 2 to the 5th, right? Do 2 to the 5th instead. So it's exponents. So we're going to take whatever our common ratio is, because it's called a ratio when it's geometric terms. It's 2, and we're going to raise it to a power. And I'm going to tell you right now it's n minus 1, and then I'll show you why. Okay. Okay. If I just used the power n, don't erase yours, but let me just say I did it. If I just used the power n, and I put in 2 to the 1, what would I get?
2.
I'd get 2, right? And then I've already got a problem because I don't have a 2 in my sequence. That sort of feels a little bit funny, right? I want to do n minus 1, and the reason I want to do n minus 1 is because what happens now when I plug in 1? What do I get? I get a 0 exponent, and what is 2 to the 0? It's 1, and 1 is easy to work with because I can do anything I want to it. Well, what do I want to do to it? Well, I want to multiply it by whatever the first term is, in this case 3. So the number that goes in front will always be the first term. The number that's in the parentheses will always be the common ratio. And the exponent will always be n minus 1 because it resets it back to the first term location. And again, you can check to make sure you did it right by choosing another one of your terms. Let's say you chose 3. You're going to look to try to get the third term. What's the third term in this sequence? 12. So let's plug in 3 and see if we get 12. If I raise 3, so do 3 minus 1 is my exponent, I get 2. What's 2 to the 2?
4.
4, that's 4. And then what's 4 times my 3 at the beginning? 12. Was that what I was supposed to get? Yeah, it is.
Sorry, what did you say that n minus 1, like what's it called?
The n minus 1 is the exponent. Mm-hmm.
But like where does it come? Like I know the 3 is the
It
first
comes
term.
because it's resetting. The exponentials are coming because you're multiplying by 2 multiple times.
Oh, okay.
I think I said that funny, but multiplying by 2 multiple times. And then the minus 1 part of it is because you're resetting it so that when I plug in the first term, I get the term at the beginning to be 1. And I can multiply it by whatever the beginning term is. Yes?
So in front of our 2 to the 12
Mhm.
one, it's always going to be the beginning number in the pattern. So
Exactly.
the only number that really changes is in.
Yeah. The only one, not n, but the only thing that changes depending on the first first value will always be your first term. And the part in the parentheses will always be your ratio. And that will change every time. I mean, those two numbers will change depending on your sequence every time.
Yeah.
And then the n minus 1 stays constant, actually. So it'll always say n minus 1 on the exponent.
Yeah, okay.
Okay. All right, now here's your question. I told you we're going to come back to this inductive-deductive business. Inductive-deductive. Is this inductive reasoning or deductive reasoning? So let me go back before anybody shouts out any answer. Let everybody think for a sec to decide if they can figure it out themselves. Inductive means making generalizations based on patterns. Deductive means using equations, axioms, theorems assumed to be true. What kind of reasoning is this? It is inductive. We took sequences and we generalized what we thought was happening in them, and we created our best guess, our conjecture of what we think is happening when we created those general terms. So this is inductive reasoning. Yes, ma'am.
So, but n minus 1 is deductive, right? Because you told us like that's the equation.
I didn't give you an equation.
Or that's
We created the equation every time. The n minus 1 is how we we deducted it. We used inductive reasoning to deduce that that's what we thought was happening. It's multiplication, so it multiplies by itself. We did a -1 because we wanted to reset it back to the beginning.
Okay.
It's still our induction of what's happening. And, you know, we're making assumptions that the pattern continues, and it continues the way we think it does, right? We'll talk more about that later. Okay, different problem now. These are nth terms. These are the equations that we created from part C, and that's where we're going to start on this problem. Using the nth term given, we're going to find the first 5 terms of the sequence, and then on part 2, we're going to decide if the sequence is arithmetic, geometric, or neither. So, what do you think we do to find the first 5 terms of the sequence? Yeah, we plug in 1, 2, 3, 4, and 5. Okay? So if we plug in the number 1 here, what do we get for the first term?
11.
So 5 times 1 plus 6, we get 11. If I plug in 2, what do I get? Is it 16 or 18? 16. Okay. If I plug in 3, what do I get? 21. Does anybody see a pattern in my 11, 16, 21 just yet? It's adding 5 every time, isn't it? So you could actually keep going with that, and it will work, or you could go ahead at this point and just do the next pieces. Why in the world, though, from the equation, do you know that you should be adding 5 every time? Because it says 5 times n, right? That's why it's doing it. Okay, so this is part A. Part B, I don't know, these are not A's and B's, I'm sorry. They're I and double I or something like that. They probably were on the last problem too, weren't they? Sorry. Okay, so this is I and double I. Is it arithmetic, geometric, or neither? It is arithmetic. Why? Because you're adding 5 every time. All right, how about the next one? Well, we're supposed to plug the numbers in, right? So it's 1 squared minus 1 gives me 0. 2 squared minus 2 gives me, minus 1 gives me 3. 3 squared minus 1 gives me 8. 0, 3, 8. So I don't see a pattern yet. How about 4 squared minus 1? 15, I heard somebody say. 5 squared minus 1. 24. Okay, so we have 0, 3, 8, 15, 24. Is it arithmetic, geometric, or neither? This one's neither. It's not arithmetic because I'm adding and I get adding 3, adding 8. Adding 5 to get to the 8, adding 7 to get to the 15, adding 9 to get to the 24. That's not arithmetic, right? Adding different number every time. It's not geometric because I can't multiply 0 by anything and actually get 3. There's no way to do that, right? So this one's neither.
Even if it is adding, you just said it isn't consistent.
Correct, which makes it not arithmetic. But, you know what? I'll mention it here now first. But it does have a different pattern, which is what Emily's mentioning. So let me go to another screen and I'll show you about that a little bit. Let's take what we had there, and I want to explore it just a little bit. We'll explore a similar argument later on another example too. So this is plus 3, plus 5, plus 7, and plus 9, right? They don't all match, so it's not arithmetic. But there is a pattern, right? What would I have to do to get the next term? Plus 11, and then plus 13. There is a pattern. And if you keep going far enough, even if you didn't recognize the pattern eventually, you would notice that these eventually all match. Okay? There's a name for what this is. This is called first differences. The difference the first time you do it. These would be called second differences. And the second differences in this sequence match. Now we're going to see an example later where it might take until the third or the fourth time comparing down like this, sort of building down this table or something. And you have the third differences that match or the fourth differences that match. So it doesn't make it arithmetic, but it does mean that there's a pattern there that's not arithmetic or geometric. It's still a pattern. It's just not got a name for it, okay? Okay, let's go back to that slide that we had before. Is this inductive or deductive reasoning? This one's deductive. We are given equations, assumed to be true, and using them to generate something specific. That's deductive reasoning. All right. We used this word at the very beginning, counterexample. Without looking, does anybody remember what counterexample means?
It's proving a conjecture false.
Proving a conjecture false. Okay? So this kind of a conjecture is the kind of things that I see on occasion with people's work. N plus 5 divided by 5 equals n plus 1. Okay? Or they might tell me it equals n. That might be a conjecture I was told as well. So the first thing we're going to do is we're going to show a counterexample. So we're going to create an example, and what that means is finding a natural number n for which this doesn't work. And it's not very hard on this one to create a counterexample. Somebody give me an example for n that will not work here. 6, 5, something. How about, can I do 5? I want to do 5. Just because it'll divide evenly. So here's how we're going to show that it doesn't work. We're going to put it in on both sides of the equation, or proposed equation, and we're going to show it didn't work. So on the left-hand side, 5 plus 5 is 10, and 10 divided by 5 is 2. And on the right-hand side, I've got 5 plus 1, which is 6. And the last I checked, those don't equal each other. So this would be a counterexample. It's an example showing that something is false. I often will have examples where somebody uses the square roots inappropriately. And so they'll want to do something like this. They'll have this like a square root of a squared plus b squared, and they'll want to tell me that this is a plus b. It's very common. It would be nice and natural and wonderful if it worked. And I do this exact same thing that we just did on the first part A of this, is that I give them numbers and show that it doesn't. And I have, specific numbers that I know that work nicely, and the fact that it's a square root and everything to use. I use the numbers 3 and 4. Because on the right-hand side, I get 7. And on the left-hand side, I get 3 squared plus 4 squared, and I simplify it, and I end up getting 5. And 5 is on the left, 7's on the right, it doesn't work. So counterexamples are a really good way to show somebody's thinking incorrect with a concrete example. Okay? So, going back to this particular problem, if you're taking a look at this, what reason do you think that someone might have for believing that this conjecture is true? In other words, what are they misthinking? What are they doing wrong to think about that?
They're canceling the 5s.
They're trying to cancel the 5s, right? And the problem is that they forget that that n on top is also divided by 5, right? So, they could cancel the 5s. That would be okay. But if they did, they would be left with n over 5 plus 1. Because each piece would have to be divided by 5. So we can divide the 5 by 5, no problem. But we need to remember also the n has to be divided by 5. But talking about what we just did on part B is not always helpful. Sometimes, for some students, it is. But a lot of times, just a concrete example that shows them this doesn't work is a better place to start than explaining why it doesn't work. okay? All right, figure-it numbers. Figure-it numbers are based on geometric patterns. It's visual. These are examples that are neither arithmetic or geometric. Such numbers can be represented by dots, arranged in the shape of certain geometric figures. So the first one we're going to do, and this is where we'll pause today after this one, is triangular numbers. All right, so you're going to make some dots, and I'm going to make mine here too. Triangular numbers. So the pattern looks something like this. We've got one dot, and then we have three dots like this, and then we have I made it too big, sorry. 4 dots is what I meant to do, and I got carried away. 4 dots on the bottom, like this. I'll do one more. And then I have 5 dots on the bottom. And we could talk about the pattern continuing, right? And you can see what you're doing, sort of creating this sort of a pyramid or triangular shape by adding one more level on the bottom every time. It's one bigger than one before. Okay, so these are triangular numbers because they create a shape of a triangle. That's why. If we were to calculate or to count up the dots in each of them, we could create a numerical pattern to represent this. So the first number would be 1, because there's 1 dot. How many dots are in the second number? 3. And how about the third number? 6. How about the next number?
I think the one in the middle was
What's that?
I think the 6th one accidentally got left out.
Did I leave out the 6th one?
I think that's why I went pause.
Oh my goodness. No wonder you guys are looking at me like I'm crazy. All right, let me put it in, I guess, if you insist. Here we go. Is that better? There's 6 dots. 1 on bottom, 2 on bottom, 3 on bottom, 4 on bottom, 5 on bottom. I want to skip from 2 clear to 6. Wow, 5? Okay. All right. 1, 3, 6. What's missing now? Or what's next now? 10. Thank you. What's next? 15. Now, even without drawing it, you should be able to tell me what would come next, because you know how we're creating the next diagram. Be 21. What is it that we're doing that makes you know it'd be 21, Ashley?
Taking was already there, and then you're adding another line that has 1 more.
Right. So the previous line had 5. The next line will have 6. So I'm just going to add a 6. And if I want the next term, I'd be adding 7, and then I'd be adding 8, because all I'm doing is adding 1 more dot on the bottom of what I already have. It's not Fibonacci, because Fibonacci means that we add the number to the previous number, not to the previous sum of numbers. Yeah. But I will show you something cool on this that you have already seen before. So don't put away just yet. I want us to take this series of numbers. I'm going to move to a different screen. This one right here. If I have 1, 3, 6, 10, 15, I know I got it by doing +2, then adding a 3, then adding a 4, and then adding a 5, and so on. It's not arithmetic, but if I go one deeper, if I go to the second differences do match, right? They do match for figure-it numbers. Second differences. So when you're looking at a pattern, if you're doing the pattern and you're not seeing that immediate, like it's adding to the next thing, go one deeper. Go one deeper beyond that. See if you can get it to where you do have that common difference somewhere down in these differences that you're calculating. All right, we're going to stop there today and we'll pick up with square numbers next time.